Hello, welcome back to Math 332. In this video, we are going to talk about the concept of bases and dimensions. In particular, we are going to look at a problem which is very similar to your problems number 6 in your homework and number 7. Alright, to get things started, let us recall the definition of a basis. So suppose you have a vector space V and you have a collection of n vectors, V1 all the way to Vn. We say that these collections form a basis for this vector space V if and only if the following two conditions are satisfied. Number one, S has to span V. Number two, this vectors here has to be linearly independent. Alright? Now, one of the consequences of having a basis is that for every element V in this vector space, this V can be expressed in this form. That is to say that V is a linear combination of vectors V1, V2, all the way to Vn. And not only that, this representation is unique. That is to say, there's one and only one way you can write V equals to C1 V1 plus C2 V2 all the way to plus Cn Vn. All right, all these numbers here, all these coefficients C1, C2, all the way to Cn are uniquely determined. All right, so because of that, we can define the concept of a coordinate. So we say that this vector V has a coordinate C1, C2, all the way to Cn. These are the coefficients here, okay, in relative to this basis S. All right, so vector V relative to basis S has the following as its coordinates. All right. One thing I want to comment is that the elements of the vectors could be things like matrices, could be like polynomials, could be like functions, but regardless of how the elements in the vector space looks like, the coordinates is always an array of n numbers. It's always n real numbers. C1 is a real numbers, C2 is a real numbers, all the way to Cn here, they are all real numbers, regardless of how the elements of that vector space looks like, okay? Now, for a vector space, let's say R2, we know that it has a basis, but the basis need not be unique, okay? The basis need not be unique. So for example, we have seen that in R2, S1 here is a basis. These are called the standard basis. And S2 here is also a basis. That is to say that these elements here are linearly independent and the span of S2 is actually R2. So in a vector space, the basis need not be unique, okay? Same thing here in the vector space P3, the polynomial of degree at most 3. You have shown that in homework 6 that this sets S1, this collection of 4 polynomials, 1 plus x, 1 minus x, 1 minus x squared, 1 minus x cubed, actually form a basis for P3. And it is also very easy to verify that these collections of polynomial, constant value polynomial, the polynomial x, the polynomial x squared, and the polynomial x cubed also form a basis for P3. So the basis for a vector space need not be unique. All right, again, one more time. In homework 7, you have asked to show that this following 4 matrices, okay, these following 4 matrices form a basis for this vector space M2 by 2. And it's also very easy to justify. In fact, it's very easy to see that these collections of 4 matrices here also form a basis for this vector space M2 by 2. So what I'm saying is that for a vector space, the bases need not be unique. They have multiple different bases for a vector space. All right, so in R2, you have, for example, these 2 different bases. In P3, you have these 2 different bases. In M2 by 2, you have these 2 different bases. However, even though the bases need not be unique, the number of vectors in the basis is always the same. All right, let me say that again. So the basis need not be unique, but the number of elements in the basis is always the same. For example, here, these are 2 different bases, but the number of elements in this basis is 1 and 2. 1 and 2, they are always the same. Here, the basis, okay, for P3 need not be unique, but the number of elements in the basis is 1, 2, 3, 4. So there are 4 elements in the basis. Here, same thing, 1, 2, 3, 4. There are 4 elements in the basis. Here, the basis for M2 by 2 need not be unique, but the number of elements in the basis is always the same, 1, 2, 3, 4, 1, 2, 3, 4. And these numbers are known to be the dimensions. It's defined to be the dimensions of the vector space. So because of that, we say that R2 has dimension 2. We say that P3 has dimension 4. 1, 2, 3, 4. Okay, and in M2 by 2, it has dimension 4 also, because the number of vectors in the basis is 4. 1, 2, 3, 4. Okay, right. So this is actually a theorem given in 4.5.1. This theorem here, we say that all bases for a finite dimensional vector space have the same number of vectors. So the number of vectors are the same, and the numbers of vectors in that basis is called the dimensions of a vector space. All right. So these are all the necessary background in order for you to answer questions that looks like this. So in these problems, you are given a vector space. This is actually a vector subspace. This is actually a vector subspace of R4. You can verify that easily. This is definitely a subset of R4. These are the elements A, B, C, D. They are real numbers, but A cannot be any real numbers. A actually has to be C plus D. B cannot be any real numbers. B actually has to be C minus 2D. You can verify that this is actually a vector subspace of R4. The question is, what is the dimension of this vector space, right? What is the dimension of this vector space? So how do we answer questions like this? Well, one way to do it is to find a basis. Is to find a basis for W. Once you have the basis for W, you just have to count the number of elements in that basis. Okay, so the number of elements in that basis will give you the dimension of that vector space. So how do you find a basis for this vector space W? So you look at A, B, C, D from W. You take an element A, B, C, D from W. You know that because it is in W, the A has to be C plus D, the B has to be C minus 2D, and C and D is real numbers. They are any real numbers. And this can be written as this, 1, 1, 1, 0, C, and then 1, negative 2, 0, 1, C. You see that? 1, 1, 1, 0, okay, that is C, and then 1, negative 2, 0, 1 for the D. All right? What this thing means is that these elements, any arbitrary elements from this set W can be written as a linear combinations of these following two vectors. Okay, let me say that one more time. These elements here are fixed elements from this set W. Any elements from this fixed set W, any fixed element in the set W can be written as a linear combinations of the following two vectors, 1, 1, 1, 0, 1, negative 2, 0, 1, which means that the span of these two vectors give you the vector space W, right? The span of these two vectors give you the vector space W. And once you have that, you can easily verify that these two vectors are actually linearly independent. You just have to use the definitions, set it k1 multiply this vector plus k2 multiply the vector, set it equal to 0. And then you can see from the last row here, your k2 have no choice but to be 0. Your k2 have no choice but have to be 0. Once your k2 is 0, your k1 will have to be 0 in order to have this multiply this equal to 0, 0, 0. Okay, so this means that these two vectors here are actually linearly independent. So these two vectors span W. These two vectors span W, and they are also linearly independent. Therefore, these two vectors actually form a basis for W. These two vectors actually form a basis for W. Therefore, what is the dimensions of this vector space? Well, you just have to count the number of elements in that basis. Obviously, there's 2 elements in this basis. Therefore, the dimensions of this vector space is 2. And that is how you solve a problem like this. You try to find the basis for that vector space. And once you have the basis for that vector space, the number of elements in that basis is going to be the dimensions of that vector space. And that's the end of this video.